Okay, then we shall continue to just make a review out of the topics. So the second order, as the name implies, I think we did also for the homogeneous. So we won't go to that again. The homogeneous case is when you have the Rx over here is equal to 0, and that should be not a problem. And then we continue when the Rx is not 0, but we started with a simple case where you have a constant coefficient on the left side, so that you'll be able to still utilize the method that we use to solve the homogeneous, except that this is not equal to 0. And also a good concept to hold is the solution for the non-homogeneous consists of solution of homogeneous and other particular solutions. So we should be able to utilize the solution for the homogeneous. As a matter of fact, it will or they will become basis for the overall solutions. Means like if you already have the solution of the homogeneous one, and then you find another solution from the non-homogeneous solution, then they should be combined. The solution will be a linear combination of the bases, and the bases are from the solution of the homogeneous and non-homogeneous. So those will still be used. And for the non-homogeneous one, the simplest one again is when you have the constant coefficient on the left side, so that what step you need to do after that is to go to a table which lists the form on the Rx and the possible solution for the non-homogeneous one. This table is what I meant. So if you have y double xn plus a y prime plus dy equal to Rx, for example, and the solution will be based first on the homogeneous solutions, means like this is equalizing this to 0. So you're going to have two solutions from here. First, you need to find where this is equal to 0. And second is Rx is when you have yp is equal to the combination of this. That's called the method of undetermined coefficient. But there are rules to follow when you do that. You see over here, the basic rule means like if you have that the YH is not equal to any of the YP. So you use that. But if you see that YH, the solution for the homogeneous is happen to be also the solution for the non-homogeneous, then you have to multiply YP by X or X squared, so that they're not going to be the same from the homogeneous solution. So they have to be like independent solutions. So you have Y1, Y2, Y3, Y4, and so on to be the independent combinations, independent bases on it. And rule number 3, sum rule. If you have the Rx is not a single function, means like the has summation or subtraction rule terms, then your choice of YP or the solutions are also combinations or summation of subtraction between the functions on Rx. So this is example that discussed also on the video. I will go just very quick over here, just a review. As you can see here, this is a non-homogeneous second order ODE with a constant coefficients over here. This is a constant. And you have this Rx in form of exponential functions. So step the same, you find first the homogeneous solution by forming the characteristic equations as lambda squared plus 3 lambda plus 2.25 equal to 0. And I think this is also useful when you're going to deal with the higher order, means like third derivation, fourth derivation, and so on. As long as they are homogeneous, you still be able to utilize this form of characteristic equations. We will discuss that later on the higher. If any of you have viewed the last videos, it discussed the higher order ODE that also going to utilize this characteristic equation method. So we find first the solution for the homogeneous ODE, and then as you can see from this particular problem, you're going to have a double root, two real roots, some real roots, which is a negative 1.5 over here. So lambda 1 is equal to lambda 2. So the form is C1 plus C2x e to the power minus 1.5x. This is actually the almost like the second rule, but for homogeneous one. You cannot have C1 e to the power of minus 1.5x plus C2 e to the power of minus 1.5x. You're going to need to put additional term over here to have to have two independent solutions or two bases, which is e to the power of minus 1.5x and then x e to the power of x e to the power of minus 1.5x. Okay, so we get this one, and then the second step is to find the solution for the non-homogeneous ODE. That case, we need the method of undetermined coefficients. We do that by take a look on the Rx, this one over here. We can go to the table. They are in this form. So the solution will be in this form also, which is exponential functions. So we determine e to the power of minus 1.5x is the Rx. So the form will be somewhat like this, which is c e to the power of minus 1.5x. However, this form of YP has been used, exists on the solution of a homogeneous one, which is C1 e to the power of minus 1.5x. So we can't use that. And the second modification, the second rule or the modification rule said that you need to multiply that with x. Then you multiply that with x. But again, this has been also used by the homogeneous solution, which is C2. In that particular case, then we need to move on to multiply that with the x squared. So again, so this becomes C3 and this is become x squared. So that's why this form take as this, cx squared e to the power of minus 1.5x. Now we have already 3 solutions. That should be form the complete solution, but still there are unknowns on the solution, right? So the solution will be c1 plus c2x plus c3. In my case, is I'm using c3 x squared times e to the power of minus 1.5x. Now we need to solve. We need to solve for the unknown c1, c2, and c3. We do that specifically for c3. We actually can solve that with the without the initial values. So to solve for C3 in this example, we use capital C over here. We just need to substitute back the solution into our original equations. So in this one, we need to have yp prime, which is, if you derive this, it will have 2x times c. This is again just like this is if you say this is like u and this is phi. So u times u prime times phi, and then phi prime plus phi prime times u, just like the derivations for the summation of functions. And this will become this, the y phi prime, and then you again derive that for to get the second derivation term. This will become y p double prime c times 2 minus 3x minus 3x plus 2.25 x squared times e to the power of minus 1.5x. And then we substitute these 3 terms into this our original equation. So you're going to have y p double prime over here plus 3 times y p prime become over here plus 2.25y become like this. Is equal to negative 10 e to the power of minus 1.5x. You cancel all the e to the power of minus 1.5x for all of them. You divide with that. So you're able to get into this. And then having this term, you can just do the same power terms. You have x squared term. You need to multiply all of this first. Or you can just take a look on the x squared term will be. Any question? Okay. So you have over here 2.25 c, and then you have over here negative 3 times 1.5, and then plus 2.25 c will be the x squared term, and those give 0, and also this is giving 0. The coefficient of x, you have minus 6c, and over here you have 6c, so they become 0, and on the right side is also 0. On the term of constant, we have 2 times c, 2c over here, and then this is 0, and then this is 0 is equal to negative 10. So 2c is equal to negative 10, you have c equal to negative 5, then you have this, and then you can substitute that into this original expression for the yp. So you have a final solution for the yp over here. And if you substitute back, you have the general solutions of this second order non-homogeneous ODE. Well, on this particular problem, you are required to find a particular solution. So you're going to utilize these two initial values. You substitute them into this equation to get what C1 and C2. If you do that, then you find that y prime is equal to this, just the derivation on that, and then you substitute y0 equal to 1, which is equal to C1 in our case, and then y prime 0 equals to C2 minus 1.5 C1, which is equal to 0 according to the initial values. Then you can also find C2 over here. So that will give us the particular solution as case. And if you draw that, if you sketch, this will be like this. So it is the case. For if this is a spring and mass system, you will see that this is conditions of overdamp, so you won't have any oscillations. Once it starts moving, then it becomes damp back into original position. Okay, so that's the case of the solution of non-homogeneous second order ODE. Is there any questions regarding this problem? Okay. So this is another problem that we have. So it is interesting to see this as a spring mass system because that is a good example of what a typical problem on the mechanical system where you have the vibration. For this case, for example, the only difference form is the Rx on the right side. And if that's a spring and mass system, it represents the external force, or we call it also the excitation force. So you have a spring mass system and a damper, and then you have an external force acting on it. So that and the force can be a constant, okay, or it can also be a function itself. So in our case, it's an exponential function. Okay, so for this problem, I think we have the same method. First, we need to solve for the homogeneous one, and we do that by equalizing that into 0. So you will have the characteristic equation of lambda square minus 4 lambda minus 12 equal to 0. So that you can do factorization, so will become r lambda minus 6 and then lambda plus 2. So you will have the homogeneous solutions as C1 e to the power of lambda 1 become, let's say this is minus 2 t. Okay, and then the other one is plus C2 e to the power of 60. Okay, so that is the solution for the homogeneous one. And then for the YP, the choice of YP according to this will be, let's say this is become C e to the power of 5t. Okay, and for this case, we don't have any similar form from YH and YP. So from that case, we just going to utilize the, we don't have to modify this. So this will become the basis of your YP solutions. But we need to find what C is in our case, or capital C in our case condition. Then you do the same things, you find the derivation YP prime, and that will become 5 C e to the power of 5t, and then YP double prime will become 25 C e to the power of 5t. And then if you substitute those into our original ODE, then will become 25 C, and then minus 4 times Y prime become, I'm sorry, this is not 20, this is 25, right? And then 4 times, let me write it so you can get it later on. 5C minus 12 times C, and then it should be multiplied by e to the power of 5t is equal to 3 times e to the power of 5t. So it be 25 minus 20, 5 minus 12, so it's become minus 7. C is equal to 3, so that you have C as minus 3 over 7. So that your general solution, because we not required to find a particular solution, so your y is equal to YH is C1 e to the power of minus 2t plus C2 e to the power of 60, and then minus 3 over 7 e to the power of 5t over 2. So this is going to be your general solution for that ODE. Any questions? And then if you require to sketch that, so that this is also going to be an underdamped, sorry, overdamped spring and mass system. Okay. No questions? Okay. Well, this is just the modification out of it. In this case, now you have the initial value conditions. So you will be able to solve our previous solutions that you get y equal to, before we have C1 e to the power of minus 2t plus C2 e to the power of 60, and then minus 3 over 7 e to the power of 5t, and then you have two unknown over here, and then you have two equations over here. Then you should be able to solve this. I think I will just leave it that for you to do as an exercise. Okay, let's continue with this one. Okay. Do we have Alfian with us? Alfian, can you unmute yourself? Alfian Koiri? Okay. So you're not there? How about Gali? Gali, are you there? Gali Surya Kusumo? Okay, Gali is not here also. Joseph? Joseph, are you, can you hear me? Okay. It's good to have a roll call just to make sure that you attend the session or not. Irfan. Irfan Zidni.
Yes, sir.
Okay.
Hello.
Is this Irfan? Okay, good, Irfan. Irfan, can you suggest what is the choice of YP on this particular case? What will be YP?
Wait a minute, sir.
Right, yeah, take your time. So as you can see, the homogeneous solution is still the same, which is you have the YH is the same problem from the previous one. So the YH we should be able to get it quickly. But what about YP? We have different YP on the right side. And you suggest any choice of YP?
For the YP to be inputted, is it different from like lambda kuadrat minus 4 lambda and stuff like that? Beda ya, sir?
No, it's different because the homogeneous one, you have that solution already. This is the same problem like what we have on the previous example. So the solution for the homogeneous one will be C1 e to the power of minus 2t and then C2 e to the power of 6t.
Oh yeah.
That was obtained from the characteristic equation. But for the YP, you need to take a look on the table. What will be the choice of YP? You have any opinion on that?
N equals 0, 1.
Okay, can anyone raise hand? So if Irfan cannot do that, we fine and fine. At least you pay attention on this.
Sorry, sir.
No problem. Okay, anyone can raise hand to answer the questions? What will be the choice of YP over there?
Can I answer, sir?
Can you raise your hand so I'll be able to, because I cannot, who's because I really cannot see who raised the hand. Okay, Daniel?
Is the choice for YP K cos omega x plus M sin omega x, sir?
Okay,
Because it's
so let me rewrite again. Go ahead. So you have what's your choice?
the K.
Okay, okay. Yeah, but it's only constant. You can use A or
Yeah,
B or K.
I prefer to use A. You can okay.
K.
K cos omega t
Mhm.
plus M sin omega t.
Okay. Yeah. So this is actually based on the table, yeah, which is this part over here. So you see that the Rx is in the form of this. Then your choice will be this form. Thank you, Daniel. Okay, go back to the problem again. So since the Rx is in the form of this, let me, so it was Daniel William, yeah?
Yes, sir.
Thank you. Okay, we can continue now. So the choice of the YP is equal to this. So what we need to do just to solve that YP, because we already have the solution for the YH over there. So in that case, we have the omega in this case is, oops, the problem should be this part. Yeah, this one. So to be more specific, the omega you can just change with 2t over here. So this will be your choice of solution. And from this knowledge, you're actually able to combine that to find the solutions. But we need first to figure out what will be the constant on the YP over there. Then if that in that particular case, you can find by having YP prime and then YP double prime from here. If we differentiating those into our equations, YP prime will be, you derive that will become, let's see, take a look on the table first. So K over here plus M sinus omega x. So in our case, we just, the YP prime will be that you derive this one become 2K sinus 2t, but it's become negative. And then the derivation will become plus 2m cosinus 2t over here. And for YP double prime, so it's become minus 4k, sorry, it's become cosinus, plus this become negative 4m sinus 2t like this. And then if you substitute back into, so you have knowledge of this YP prime and YP double prime. So be like we are dealing with this one. So what you need to do just to substitute all of them into this, and then see the term that is related to. Okay. So let's do that. Let's try to so the Y double prime will become still Y double prime like this. So minus 4k is for the next term, for the next time when you do it, you can actually take a look on the coefficient only. For example, if you see there is no cosinus on this part, you can just cancel that. You can just ignore that. But for this point in time, just to show you the step, I'll go with the more detailed one. So negative 4 cosinus 2t minus 4m sinus 2t, and then you minus 4y prime. So it's become minus 8k sinus 2t, and then this is minus 4 plus minus 4 times 2 become minus 8. Sorry, plus, yeah. This is minus, this become plus, and this become minus 4 times y prime become minus 8 k, sorry, m should be m, cosinus 2t, and then the minus 12y become minus 12k cosinus 2t, and then minus 12 m sinus 2t. Then this will be equal to sinus 2t omega. So since there is no cosinus term, and you will see that they will also going to be cancelled on the cosinus term, so we can just deal with the, take a look on this one, minus 4 cosinus 2t. So this become, what you can do, you can just, what's the coefficient of cosinus 2t over here? On the right side, you have 0. On the left side, you have minus 4k, and then minus 8m, and then you have minus what else? 12k, minus 12k, and then that will be equal to 0. And you can also do for the sinus one to get the sinus coefficient. But there is one trick over here. If you take a look on this, we can also just take the sinus term on the solutions on this one too. And then for this, once you get the solution for the non-homogeneous solution, then we will have that minus 16k. So over here, so this is 0. So you have over here minus 16k minus 8m equal to 0. And then the sinus term, sinus 2t term, will become 8 k, and then minus 16m. This is equal to 1 because the coefficient over here is 1 over. So you will have 8k minus 16m equal to 1. And then you can solve for k and m. You have k equal to minus 1 over 40, sorry, 1 over 40, and then m is equal to negative 1 over 20. Then you can substitute this value back into your solutions, which is this. So I will delete this one. So this become 1 over 40 plus or negative 1 over 20. And then your general solutions will be combination of between these two. So y equal to yh plus yp. Okay, so that's the case. Any questions? Okay, very good. Okay, let's continue. Another combinations is Theodore Binsaris. Are you here with us? Okay. How about Paulus? Paulus is not here. Okay, Muhammad Aksa, can you unmute yourself? You can unmute yourself, right, in your case. Okay. Gifari, are you with us?
Which Gifari?
Oh yeah, sorry, Gifari Ahmad.
Yes, sir.
Okay, Gifari Ahmad. Do you have any suggestions on the choice of YP in our case?
Is it kn x power of n
Okay,
and so and so?
okay.
So
you have YP as equal to K? Is that what you say?
kn
N?
x power of n.
Okay, so Kn like this, yeah?
Yeah.
X to the power of n.
Yep.
Well, this is actually the general form, but thank you very much. I appreciate it.
Oh, okay. Sorry, sir.
No, that's good actually. How about Muhammad Rifki Putra Wijaya? Are you there with us? Muhammad Rifki. Okay. Raffi Yusuf Adrian. Oh, is Rifki there? We cannot hear your voice actually. Okay, Raffi is here. Okay, Rasendria Sajana. Not here too. Putri Parahdita. Abad Rasa Aladino Rayendra.
Yes, sir.
Okay, Rasa. Can you be more specific on the YP choice over here? This is already correct form, like Gifari Ahmad mentioned previously. But can you give any more specific form on that? Okay, so do you have any idea, Rasa?
No, sir. I'm sorry.
No? Okay, no problem. So this is the correct form, like the Gifari mentioned previously. But you see, they already have n over here, and then our solution over here is the n value is equal to 3. So in our case, YP should be in the form. So this is Kn. So this is, you have K3 over here. And then you have T to the power of not X, but T to the power of 3. And then you have plus K2 times T squared. And then plus K1 to the power of, in our case, is T only. And then plus another constant, let's say K0. So this will be your choice of yp. Okay. And then the next step will be to get yp prime and then yp double prime. Do we have Bagas Tegar with us? No. Do we have Fauzan Naufal?
Present, sir.
Okay, Fauzan Naufal. What will be the yp prime? It's so easy. Yp. Now you just derive the this equation. What do you think, Fauzan? Hmm? So for this case, remember K3 is a constant. So what you need to do is just to have 3K3 t to the power of 2.
2. Oh yeah.
And then what else?
Oh.
Next? What will be next?
And then 2 2k to the power of no just t.
T and then plus
And then and
plus
then
K1.
plus k1. Yeah.
Okay,
That's
good.
it.
Yeah, thank you. Do we have Ignatius Adrian with us? Ignatius, are you there? Okay. Muhammad Rifat Muntas?
Yes, sir.
Yeah, go ahead with the yp double prime. What will be the
Okay,
yp double prime?
so it would be 2 times 3, so 6k3t and 2k. Yeah, 2k, 2k2.
2K2. Remember, there are different values. K3, K2, K1, K0 are 3 different values. So you don't miss the index over here.
Yes, sir.
Okay, so and then once we have that, we just need to substitute this over here of the 3 to the our original equations. So we're going to have yp double prime as 6k3 t plus, but I think I'm just gonna skip this part. So what we can do is to what do you call, to equalize the coefficient on this one. Okay, let me write that. I think we need to do that step in a way. Six K this is T and then plus 2K2 and then minus 4 times 3 means 12. T square and then minus 8 K2 T square K T on only, and then plus K1 minus 4K 1 over here. And then the yp itself, this is minus 12 yp. So minus 12 K3 and then minus 12 K2 T square and then plus, sorry, it's again also minus K1 T and then minus 12 K0. And they are equal to this. So what you're going to do is to equalize the exponent. So first exponent of t to the power of 3. Let me Muhammad Gifari Rizki. I think you're there also.
Yes, sir.
Yeah, Muhammad Gifari Rizki. So what will be this step continue with? What's the coefficient of t cube according to this, according to our work here?
Which one, sir?
Here, what is the coefficient of t cube?
Uh, 12K3.
Only minus 12K3, right?
Yeah.
And what will be the right hand side on that? Take a look on these ones over here. You see that the coefficient of t cube is over here is equal to what?
So it will be minus 12K3 also.
No, on the right side you have 2 only. Because the right hand side is this is 2t cube minus t and then plus 3. So the coefficient is only 2 over here. So you can find K3 is equal to what value? Ifari? You just do the 2 over minus 12, right? It is equal to negative 1 over 6. Do you get it? Ifari, do you get how to get minus 1.6?
I'm still confused about the cubes equals to minus 12K3.
So this one over here, get actually from this part. Because
Okay.
that's the left side is the only one that having t cube is only one coefficient, which is minus 12k, 3. And then the right hand side is only this part. So you equalize the coefficient. Minus 12k, 3 equal to 2. So k3 is equal to 2 over minus 12 equal to negative 1 over 6. You get that?
Oh, okay, sir.
Okay. Do we have Arfadila Prenardi Adam with us? Arfadila? Okay. Muhammad Dia Andrianto? Okay. How about Muhammad Irfano? Muhammad Irfano here?
Yes, sir. Yes, sir.
Okay. What will be the coefficient of t squared on this problem?
Minus 12k2.
Okay. And then? Anything else? Here, you missed this part of it.
Minus 12.
Yeah, minus 12k, k2 and then minus 12 k3. And then does equal to what? On the right hand side. Irfano?
0.
No, it's not. Oh yeah, that's 0, right? So since we have already k3, we can solve for k2. Can you help me to find what's k2 value is? According to this equations.
Wait, sir.
Go ahead. Do you have pen and paper with you?
Is it minus 2, sir?
So no, it's not. So when you, because k3 is negative 1.6, if you substitute that, into with negative, so it's become 1. This is time 1/6 here. So that will become also 1/6. No, it's 1/6 also. Here you can have this equation and just manipulate these equations. So K2 will become 1.62. Okay, you can take a look again later on. Now I will ask Miftah Rizky Ananta, are you with us?
Yes, sir.
Okay, what will be the coefficient of T in our equation here?
Is it 6K3
Okay.
minus 8K2
Okay. And anything else?
minus 12K1?
Right, and that will be equal to what on the right-hand side? This is the equal sign of it. What is the coefficient of T on the right-hand side?
Is it 3, sir?
No, it's -1. This one over here. You get that? Because this is coefficient of T, not coefficient of constant. So this is -1. So what is T? If you substitute that, T will be equal to, sorry, not T, but the one that we can obtain from this is K1. So from here we can get K1 is equal to -1/9. Thank you, Mr. And we have Muhammad Ryan Rafiuddin.
Yes, sir.
Okay.
Yes, sir.
So what will be the coefficient of, let me, T to the power of 0, which is, we will have K0 on this.
2K2
Okay.
and then minus 4K1
Okay.
and minus 12K0.
And if that's the case, what will be the K0 then?
It's
Oh, you have to calculate a little bit on that.
equal to 3. Yes.
No, but that's fine. I think you can do that. You can calculate that. So you have minus 5/27 will be your K0. So you substitute that K0, K1. So I'm going to use different color on this one. So thank you, Mita. We'll continue with this one. So we have K0 over here, K1 over here, K2, and K3. You substitute all of them back into our original equations. So we have YP as equal to -1.6 T cubed, and then plus 1/6 T squared, and then minus 1/9 T, and then minus 5/27. Don't forget your YH. Your YH already obtained as before, C1 e to the power of minus 2t plus C2 e to the power of minus 60. So the solution is y equal to YH plus YP. Incorporate all of them. Okay, any question until this point?
I think it's clear so far, sir.
Yeah.
Clear, sir.
Okay, so those are examples for the, I think we cover 3 forms of this, right? We cover this one, we have this, we have this one already. Oh, we haven't covered this one part, but that should be the similar case on our example. Okay. So and the discussion over here is be more into physics problem over here, where you have the application on the spring and mass problem, where you're going to have this is the general form, and they are really similar with what we've been working on the example, on our previous example. You just see that this is the force that is called the excitation force that can take any other form. As a matter of fact, we already have this form in our examples, which is this one over here. So we have the tools already to solve this kind of problem, including with the spring and mass system. We're able to solve what is y as a function of time, for example. That's a great things about the previous method we discussed. We have this ready to be used. We have this kind of problem. What this problem can solve is you can find the positions at any given time. Right? You can find the position at time equal to whatever value you choose for. And there are also several interesting values where you have what we call the resonance. So again, this is the solutions. This is to derive the formula, but you don't have to do this because you know already how to solve it. And this formula, you can prove it also using your previous solutions. You can see that they can be the solution going to be combinations of the homogeneous and non-homogeneous one, and it's not going to be a superposition of two harmonic oscillations. Okay, and then there are some interesting point or positions here when you have what we call the natural frequency, which is the value of W0 over 2 pi. Okay, and W0 is obtained from the solution of the homogeneous one. Over here, K over M is W0, and the natural frequency is W0 over 2 pi. So what is the natural frequency over here? Well, it's really, well, from the mathematical point of view, it's just another number. But from the physical point of view, it's really, really important, because when you have that natural frequency, okay, it's going to isolate naturally without any forces going to isolate like that. Okay, so what will happen if you have the excitation force that works, that makes the oscillations come to the near or even equal with the natural frequency? If that's the case, you're going to have resonance, and the resonance is actually going to amplify the amplitude of your oscillations, and then that is really destructive if we talk about mechanical vibrations. Okay, so if you have away from the natural frequency, they're going to be because they are superposition, then they can decrease the amplitude. But when you come into a natural frequency, or what we call the event called resonance, then the superposition will actually amplify that, and then that will become a large oscillation happens on that. So that's why during the design of a system, for example, the turbines, gas turbine or steam turbine used in the power plant, they have vibration when they rotate, okay? And then the engineer the manufacturer first will try to design the natural frequency of the system. Means like if the system works without any load, for example. And then once you have the load, then you have excitation force from the external one. And you want to avoid that the system works at the natural frequency because of that, because of the resonance event on this case. So this is something that you want generally to avoid, to work to make the system work at the natural frequency, because the damaging is severe. So and the natural frequency can occur on the several stage depending on the, of course, for example, there is no load, you have that. When you have the load, you're going to change the frequency, and then we see we're going to see the resultants or the superpositions of those forces and the natural frequency. We measure that. So in the practical case, when you do startup, during the startup of the power plant, for example, the steam power plants in more general like that, you want to do it away from the natural frequency, but you have to go past it because you want to increase, for example, from 0 RPM to 3000 RPM for the steam power plant. To go from 0 to 3000, you're going to pass the natural frequency, and you want to do it quickly. I mean, you don't want to stay on the natural frequency too long, because otherwise, as you can see, this is under damping condition, so you're going to have the system oscillate very high, like this. So in that particular case, you have to pass the natural frequency, but you want to pass it as quickly as possible. You can increase the RPM and stabilize outside the natural frequency. So this is the application on that. There is also another one called beats, but I think it's on the engineering point of view, it's not really critical. This is for musical application, for example. And this is for the undamped oscillation, when the difference between the input and the natural frequency is small on this case. The second case, when you have damped force oscillations, means like you have the damper which is going to reduce the vibration until it's become 0 or back into its original position. And we can take a look on the curve is like this. As you can see, the bigger the damper coefficient, the faster that become back into original position. And another application of this is we have also on the electrical system, and then we can see the resemblance, we can see the analogy between the electrical and the mechanical system. So L is called the RLC circuit. So L is the inductance. So if you have a coil like that, and then if you have the resistance, and you have the capacitance, and you have this external power. And those going to have analogies with our mechanical system. So the conductance, sorry, the inductance L, it's just like the mass in our spring and mass system. The resistance is like the damping constant, and then the capacitance, 1 over capacitance, is like the spring constants. And then those the displacement Y is in form of current in the electrical system. So in our mechanical system, you want to know how the oscillations, right? How the mass move up and down, above or below our reference positions, because it relates to the force and also the ability of the material that withstand the motions. You cannot have much displacement or the material will break. But that has analogy with the electrical system. In this case, is the current. Each electrical material will have its ability to withhold certain amount of current. When it goes past its ability, the material will break. It will explode, for example. If this is too much current that it can hold, it will explode or break. Just like in our mechanical system, it has more displacement that it can hold, it will just break, failure occur. So if you are working in the electrical field, for example, or related on that, you can still utilize the knowledge that you obtain mathematically, the methodology you can solve for this. And these are the analogy. Okay, any questions until this point? Okay, I think I still have like about 10 minutes, so I'm going to go to the next examples for the method of variation parameter. So our discussion on the previous section deals with what we call the method of undetermined coefficients. And that applies only if the Rx form, this one, has the similar form on the table. But sometimes we don't have that privilege. The excitation force on the mass and spring system can take any form. So that for that case, then our method of undetermined coefficient will not suffice to be used to solve that. So we have another method to do what we call the method of variation of parameters. So this one applies when undetermined coefficient cannot be used because of the function that we have on the Rx is not listed on our table. But it is still going to utilize the solution from there. So it still be useful on that. Okay. So this form based on the theorem that you have y1 and y2 as the basis solution of the homogeneous ODE. And then we're going to utilize y1 and y2 to find another solution or other solutions relating to our problem. So that's called the method of variation parameter. So we're not going to start from zero. We're going to utilize the knowledge of the solution for the homogeneous one, y1 and y2 to solve, to find another solutions. So we utilize this formula. But remember, we can do this only if we have the knowledge of y1 and y2, which is we have from the solution of homogeneous solutions. So in here we introduce another what do you call it? Parameter, what we call the Wronxian. And the Wronxians, if we have the solution of y1 and y2, can be obtained with this formula. And all of this called the Lagrange method or the variation of parameter method to solve. Okay, so the step is, first you need to find what's YH. From here you will have y1 and y2 as your homogeneous solutions, and then you find yp, or before that you find the Wronxian from there using this formula. And then once you get the Wronxian, you can get the yp is equal to negative y1 integration of y2r divided by Wronxians dx plus y2 integration of y1r over Wronxians dx over here. So you have the solutions. Once you have the YH, YP, then you can combine all together to get the final solution on that. Okay, let's put that into example. We have non-homogeneous ODE as y double prime plus y equal to secant x, which is secant equal to 1 over cosinus x. So we see that this form is not on the table. It's not on the table in this case. Let's try. Do we have Muhammad Bintang Setia Abimanyu with us?
Yes, sir.
Okay, Muhammad Bintang, what will be the YH?
Pardon?
YH.
Oh,
Okay, maybe I will simplify the equation. What will be the characteristic equation you can suggest from this?
okay. Wait. Uh, uh, hmm. I don't have a clue, sir.
What?
I don't have a clue about the answer.
Okay. Muhammad Ilham Makarim, are you with us? How about Ada Muhammad Fadli?
Yes, sir, present.
Yeah. Do you have any suggestion what will be our characteristic equation?
Let me think for a minute, sir.
Okay. Now we have a minute on that. Okay, Putri Dita, I think you already come back. Now, if you can you suggest any characteristic equation from this problem?
I forgot about the characteristics. Sorry.
Okay, Rifki. Or anyone, anyone raise hand to help this one? My question is, what will be the characteristic equation for this problem? No one? Okay. So we actually go back to our homogeneous solution. You have this one, y double prime plus y equal to 0. So that's the homogeneous form. So your characteristic equation will be lambda square plus, you don't have y prime. So it's not lambda, but plus 1 equal to 0. So what will be lambda equal with? Anyone?
Plus minus 1, sir.
Plus minus?
1.
Nope. Square root minus 1.
Yeah.
So, or also plus minus I, imaginary. Or you can also, let me go back to our homogeneous solutions a little bit, just very quick. If you have negative, if you have imaginary solutions, then so this will make a complex conjugate, but this one is equal to 0. So you have plus minus I omega. Plus minus I omega means, so this is equal to 0. Sorry, not 0, but x equal, this one is a equal to 0. So our solution will be y equal to yh, a cosinus x plus b sinus x, because omega is equal to 1. We have this. So lambda 1 and lambda 2 in our previous problem is equal to I omega, and this one is negative I omega. On our case, omega is equal to 1, so this will be like this. So our solution is like this. The basis of solution is actually the term itself. So the basis for these solutions, we have y1 is equal to cosinus, this is theta, and then y2 equal to sinus t, or the other way around. It's okay, it doesn't matter. Okay, so let's go back to our problem. We've already found the basis. So we find y1 and y2 is equal to cosinus x in our case and sinus x. So what do we have now? We need to find what's the w, or the Wronxian. The Wronxian is formula is equal to this: y1 times y2 prime minus y2 times y1 prime. If we do that, we can get the Wronxian as this, and then this is equal to 1, because cosinus square plus sinus square x is equal to 1. And then yp, just include that into this formula, and we will have yp equal to this equations, and then you do the integrations. You can I think you can use the integration table for this case, and then you have yp equal to this. Then you already have yh from our previous discussions, and then you have yp over here, then we combine that to become yh plus yp is equal to this. So this will be your general solutions for this particular problem. So this example gives you another alternative method. If you have non-homogeneous, but the Rx is not listed on the table. So we go through a different way to do it. We use the method of variation parameter, or also called the Lagrange methods. Any question until this point? Okay, so I think this concludes the second order differential equations. We're going to discuss the higher order, but don't worry, because the higher order utilize similar methodology with the second order. If you understand the second order, so it will be easy to comprehend the higher order. So my suggestion is, before we go to the Wednesday session, you can take a look on the previous videos, especially video number 1, number 2, and number 3, that you can understand and do the homework. Homework 3 actually deals with the second order homogeneous one, but the non-homogeneous one we just discussed for today, and the video number 3 also discussed on the non-homogeneous one. So just for recap, the second order consists of homogeneous and non-homogeneous. The simplest form is when you have homogeneous ODE, but a constant coefficient. That will be the form of, let me go back home with this. This is the simplest form. It's called homogeneous second order ODE with constant coefficient. So this coefficient is constant. This just needs to form the characteristic equations. And then you solve it, you have the form, but there are rules. I mean, if you have, there are 3 rules. If you have a different real roots, you can go just directly. If you have double roots, then you have to multiply with x. If you have imaginary roots, then you can go with the cosinus plus sinus form, or in form of imaginary number. So we have 3 cases over here, and it is summarized here. First case, second case, third case. And if you move forward to the more complex ones, is when you have, and the application is for the spring system. When you have the non-homogeneous case, but still with a constant coefficient. Okay, for the non-homogeneous case, you have to combine the solution for the homogeneous and the non-homogeneous. The non-homogeneous case, we'll take a look on the table, what we call the method of undetermined coefficient, and there are also 3 scenario, 3 rules, which is called the basic rule, modification rule, and the sum rule. And then the last one is when you have non-homogeneous with still a constant coefficient, but the table, the Rx is not listed on the table. So in that case, you can use method of variation of parameter or Lagrange methods, and you work with the Wronskian component in this case. Okay, so I think that's all for today. Again, I think I'm still going to post this one, although from the material point of view, they are already available on the 4 video at AMAS, that you should watch that before the session to be able to understand that. Okay, so any question, last question before I end the session? If not, Then I will end the session. Thank you very much, and I'll see you on Wednesday. Thank you.
Thank you very much,
Thank you
sir.
very much,
Thank you.
sir.
Yes, sir.
Thank you.
Sure.